Hi everyone. Okay, so we are back today with our telescope primer, and we had yesterday basically looked at. Sorry, just a minute. Yeah. So yesterday we had looked at our setup here, and you can see there's one more telescope we have put up today with some imagers. Okay. So just before we go into that, let me quickly remind you what we have done yesterday. Let me share my screen. Okay, so in the primer that we went through yesterday, we talked about the various things, including telescopes, accessories, mounts, and today we'll come to imaging devices. Information part is basically the whole course that you're doing, in which you'll get information about what is there to observe, etc. And hopefully, when things are better outside, you can have your own telescope, or if you're in a department or you're an educator, you can gather your students around and do observations around that information which is being shared in this lovely summer course. So we are kind of in the middle here today, and after having seen various kinds of telescopes, etc., including this one yesterday, we are today going to the imaging devices. Okay. However, before we go to that, I had given a disclaimer yesterday that we may have cloudy skies, and yes, we have not just cloudy skies, but also drizzling rain here. So I cannot take this telescope outside and show you any object right now. The moon would have been very beautiful to show today, so that is not happening. However, I'll just give you a treat, and I will show you something special. Okay, so have a look at. So we are going to travel to the IUCAA Giravali Observatory, and I had promised and mentioned earlier that during regular times you would have gotten a trip to the Giravali Observatory and maybe also to the Giant Meter Wave Radio Telescope. But I'm going to give you like a few minutes trip to the observatory via video. So just hold on. I'll give you that treat in a minute. Okay, share screen again. And share. Okay, I hope you're all able to hear this.
Hello friends, my name is Bhushan Joshi. I'm an electronics engineer working in IUCAA Instrumentation Lab. Today we are at IUCAA Giravali Observatory, which is 80 km from Pune city, off Pune-Nashik Road, at the hill of Giravali, which is at the altitude of 1,000 meters from mean sea level. So let's get started. Let's move. The telescope was manufactured by Telescope Technology Limited and handed over to IUCAA after installation and commissioning on February 14, 2006. The telescope was formally inaugurated by Professor Yashpal and dedicated to astronomy community on May 13, 2006. After a phase of performance and science verification program, the observatory is opened for regular observation in November 2006. Behind me is the main telescope building and telescope room. Let's have a brief introduction about IUCAA Giravali Observatory. In addition, so finally we are on the telescope viewer. Behind me, you can see IUCAA 2-meter telescope, which is of split cassette time. Between black and blue surface, you can see a primary mirror, which has a diameter of 2 meters, focal length of 6 meters, and thickness of almost 1 foot, and the weight is 1 ton. On top, you can see a secondary mirror, which has a diameter of 0.6 meter and focal length of 6 meters. The mount of this telescope is called alt-azimuth mount, which has two motions. So one is azimuth motion, which is parallel to the ground, the telescope floor, and other one is altitude, which is perpendicular to the ground. So we have 5 ports available on this telescope. One is main port and 4 side ports. The field of view of main port is 21 arc minutes, which is slightly lesser than a full moon. When we tilt this telescope to see objects near the horizon, the primary mirror deforms due to its own weight. This minor deformation in the primary mirror resulted in a huge distortion in the image. To correct it, we have to push the mirror from the opposite side. The system used in this telescope to correct that distortion is called active mirror support system. This telescope does not have provision to connect an eyepiece. Instead of that, on the main port, we use instrument and charge-coupled devices to grab the data. Those C-series are kept at very low temperature. The temperature is almost minus 100 degrees Celsius. This telescope does not have any port where you can put eyepiece and see by your own eye. Instead of that, we use CCD cameras. The CCD cameras used on the instrument are spatial cameras which has lower noises and high resolutions. The temperature at which the CCDs are kept is almost minus 100 degrees Celsius. We use liquid nitrogen to lower down the temperature of CCDs. When starlight enters in the Earth's atmosphere, it is refracted by different layers of it. It is resulted in a scattered images in the ground-based observatories. To nullify this effect, scientists use adaptive optics technology. A new instrument known as RoboAero is currently being installed on this telescope, which will enable adaptive optics and will result in the sharpest possible images.
Okay, so yeah, hope you could hear it. There was slightly low volume in the beginning, but this is a very basic video that we are working on. I just showed you a clip of it, so hope you liked it. What we will do now is we'll go back to our session. We have Atharva and his friend Prathamesh here with some other setup. So we'll just show you the imaging devices today after I finish with my one more slide that I have to show you. So just hold on, share again. Right. So after lovely observatory, let's go back to our session. So imaging devices. Now you can use various kinds of things, anything which has the capacity to collect light and turn it into a digital information can be used for as an imaging device. Okay, you could use a mobile camera or a prosumer camera like this. You know, many of you may have this kind of a camera. This is a fixed lens. The lens is attached to the camera. It has most of the features that a DSLR has, but the lens is not interchangeable. So these usually come with a huge zoom range, and of course that brings in a lot of distortions and aberrations. But that's fine. I mean, you compromise a little bit. However, these can also be used very well as piggyback cameras on telescope mounts, or themselves they can be focused in a way so that you can take good pictures. They have CMOS detectors, so which are actually the kind of the most popular imaging devices that are there in sensors. So CMOS is a kind of a sensor. Okay, it's a MOSFET sensor. Then there are DSLRs, so digital single lens reflex cameras, which are what people often popularly call the professional cameras. In this, you can see this is one of them. This is the one we have here. It's got this feature that you can detach a lens. You can attach different lenses. It's got this mounting here, and you can detach and attach lenses. In fact, what we do particularly with telescopes, is we just take out the lens here, and then with the attachment, we directly insert this to the telescope. So therefore, the telescope itself becomes our lens, right? So we don't need to have more optics in between the telescope's secondary and the sensor on this camera. So that's a great way to do things. You get the light directly onto the sensor. Only you'll have to, of course, adjust focal lengths, and you'll have to have those attachments so that the camera can fit properly onto the telescope eyepiece holder and it doesn't fall off, because these are quite costly. This one I think is about 90,000 or 1 lakh. Price may have changed. So these are slightly costlier, but these give the best results unless you're going for charge coupled devices. So CCDs, charge coupled devices, are the ultimate in astronomy imaging, and you can get them in various types. These are extremely sensitive, and these are, of course, the raw sensor. So inside this camera is a sensor, and usually even DSLRs these days have CMOS sensors. But CCDs are even better because they have something called very low noise. So basically, any electronics creates its own currents just due to ambient temperature, okay, and due to the nature of the components of the electronics. So these currents, even if they are very feeble, compared to the dark sky, which will make zero current, a completely dark sky, and your CCD is exposed to it, should make zero current, right? But the CCD's components itself may be making some current, which will go to the information recorder as some light detected, right? Which is a false detection. So therefore, the CCDs, we like to have imaging sensors which have the least noise. Okay? This is called noise. This is not something you want. Like listening to a song, you don't want some other noise there. This is noise. So we want to have the least noise detector. So CCDs are the least noise ones because of their electronics. Also, these we usually cool them down, right? So with various kinds of mechanisms, including Peltier effect, which you may have learned, or as Bhushan just said in his video, that liquid nitrogen can also be used. You can use water, you can use liquid nitrogen, anything. There are people who have come up with various innovative solutions to cool their CCDs. Now this cooling gives you like the darkest of backgrounds and the best lowest noise images. So each dot on your CCD that you detect, you know that is light coming from astronomical sources, not from inside your instrument. So these are the best best things that you have in the market. I would recommend, as I said, I would recommend mobile cameras, even, or prosumer cameras for people who are beginning, and these go perfectly fine with your 6-inch, 8-inch telescopes. Even better if you have tracking. DSLRs are good, and they are really good for astrophotography. And in fact, they can also be used for things like photometry, or even with various filters, you can actually get them to show or do some spectroscopy. Okay, so those things are there. And then for research grade work, you have to, of course, get a CCD or or some new kind of CMOS detector which has very low noise. Okay, so these are the imaging devices we recommend for various levels. And then, of course, there are we also have observation suggestions. So these are very common things, probably easily known to you. You can begin with lunar observations. That's what we were going to. That's what we were going to do today with our telescope. We're going to go to the easiest object to find an image, and that is the moon. You could go for solar observations, but for that you have to be really careful to have a filter, and then make sure no leaking light goes into your CCDs or any of your imaging devices. But solar observations are also pretty easy to do. They can be done in the daytime even, and lunar observations can also be done either at day or night, depending on when the moon is visible in the sky. Yeah, if you don't understand what that means, you need to find out about it. So solar observations can be done during the daytime. They are a little more, you have to be careful compared to lunar observation. Then there are planetary observations, observations of, planets like Mercury right now is coming above the horizon quite a bit on the western horizon. Then there is Mars was there in the sky. Very soon it will be in the morning sky. There's Venus, Jupiter, Saturn. These are the brightest planets in the sky, and various kinds of observations are possible in which you can not just look at the planet but also maybe study the satellites and other bodies around it. There are occultations, so things going behind something else. So maybe a star going behind an asteroid passing in front of it. That's a great example of an occultation. But the simplest occultation is basically a solar eclipse, right? So you can have something as simple as a solar eclipse, or as difficult as an asteroid hiding a star behind it, and then because of the shadow that you get, you can judge the shape and size of the asteroid. So various levels of occultations can be studied with telescopes. You can go to stars, you can study their, as I said, you can study their properties. With the light they emit, you can do HR diagrams, you can do spectroscopy, you can do variable studies, so whether those stars are varying or not. And you could do astrophotography. Okay, so this is more like taking great images of the sky and also not just enjoying things but also learning more about the optics that you're using. Okay. So these are various things that you can do, and it itself will take another lecture to cover all these topics, all these suggestions, which I am not going into. But with these, I'll now finish my part of the session and pass it on to Atharva, who's waiting with us with his telescopes and his imaging software, etc. Thank you all. I'll just maybe can I take a quick question, Atharva? I can see a question which may be just be relevant. Okay. Okay. So cleaning a telescope, Atharva, you can cover that. And how do we track by mobile camera? So that's a question. Again, you can cover that, but I would just say that tracking is done by your mount. You don't track with the camera. Your camera is basically attached to the telescope, and telescope is put on the mount, which is then tracking the object. So your camera need not do that. If you're only using your mobile, you will not get pictures. You need a telescope in front of it to take good astrophotographs. So Shubham hopes that satisfies you. Atharva, please take over.
It is important that we plan whatever we are going to observe. So the best way to do that is basically using a simulation software. So I think a few days back, Prakash has covered the Stellarium demonstration for you. So
it will be covered next week, I think.
Oh, I see.
As far as I remember.
I see. So there is a software known as Stellarium, which is an excellent software which is available on many platforms, including mobile, and it is now free on all platforms. So when you install the software and you open it, the software allows you to select a location. So you just have to enter your city name, and if you enter the timing. So today we are looking at the sky for 19th of May for Pune, and the timing right now we have set is 7:28. So why do we use this software is we can plan our observations and we can select what all objects we want to set in the telescopes. So at sunset, as you can see, we have, as soon as the sun is setting, we have Venus, Mercury, we have Mars, and we have Moon. Okay, so these are some 4 very bright objects that we can easily see in the telescopes. Then as it keeps getting darker and darker, you will notice that more and more objects start to appear, and then there are further more stars. So today, if we had set the moon, if there were no rains, then the moon phase would have been a half moon phase. So I will come to the current time. And if we had set the telescope today, this is how the moon would have looked like through the field of view. The live view of the moon and the entire procedure. But this is how the moon would have looked like if we had, shared the image. So I can see that somebody has said that one of the Stellarium demos has been done. So apart from the moon, we can also see different planets and different other objects in our galaxy. So let me quickly show you a few more slides. So what I can do is I will share this series of slides with you, and this is a very good reference list of slides that you can choose. So when we do astrophotography or any kind of a photography, the most basic form of photography is a pinhole photography. So you simply have to have a very small pinhole, and that pinhole will then act as a biconvex lens, and it can produce a clear image of a very far away object. So this particular thing is known as camera obscura, and it was used for sketching in the very olden times before there were cameras. And you must have seen something like this during an eclipse, where you can see many images of the sun's current phase during the eclipse from the leaves or the gaps between the leaves. So quite a similar concept is used in a camera lens also. So there are many types of cameras. Initially, there used to be photography film cameras, and then we had photography rolls or film rolls. And further, it started to evolve, and now we have reached the DSLR era, where we use digital single lens reflex cameras. But we are not simply limited to that. There are so many more different types of cameras that you can use. So you can use a web camera, you can use a mobile phone camera. Then there is a point and shoot camera device, as well as there is a planetary camera, CCTV camera, and CCD camera. So just a few minutes ago, Samir mentioned about the CCD camera as well as DSLR camera. And we are going to demonstrate 3 out of these cameras to you and to the telescope. So this is how we actually attach the cameras directly to the telescope. So one of the ways is to set up the camera in a piggyback mount. Okay. So there is a telescope tube, which we call as the optical tube assembly. And on top of that optical tube assembly, we can directly affix the camera using a simple bolt. Okay. So there is a mounting bolt that usually comes with almost all the modern telescopes. The piggyback mounting. Can somebody quickly give me a feedback if you can see the screen very clearly and also hear me?
Yes, Atharva.
Perfect. Thank you.
You could go into present mode so that.
My bad. So this will be better. Yeah. So this is the piggyback mounting, and this is one of the ways. Another way is known as the mobile phone adapter. So you can easily purchase these kinds of adapters in the market, or you can make one. So it is very easy to make this attachment. So if you are fond of designing and 3D printing, then there are ready-made files freely available for 3D printing these different adapters. Then today we are going to demonstrate the T adapter also. So one of our telescopes outside is connected via T adapter mounting. And what it does is you have to remove the lens of the camera, and in place of the lens, you have to attach a T-ring. Okay. And the reason that this ring is called as a T-ring is because if you look at it from hatching is done in the shape of a T, the alphabet T. Then also it comes along with a 1.25 inch reducer, because it's much larger as compared to the eyepiece holder. So you need to attach a reducer to insert the camera axially and firmly into the telescope. So this is the T adapter mounting, and there is another attachment which allows you to magnify your image with the help of your eyepiece. So yesterday we learned that eyepiece is the instrument that is responsible for the magnification in your telescope. So whatever objective diameter is objective focal, you have to divide the objective focal length by the focal length of the eyepiece, and you can get the magnification. This is something which is an additional attachment called as variable projection tube or eyepiece extension tube. So it allows you to insert an eyepiece in front of the T-ring, and the image which is formed because of the eyepiece falls onto the camera sensor. Okay, so this is the DSLR camera. The eyepiece attachment scope enters the eyepiece and then falls into the camera. If there is no eyepiece, then it directly falls onto the camera. When there is no eyepiece, that type of photography is known as a prime focus photography. Okay, so you are directly attaching the camera sensor to the telescope instead of the eyepiece. So that is known as a prime focus photography. So there are too many slides. We are not going to cover many. These are the different types of mounts. So this is the equatorial mount that we saw yesterday. So the mount that you see on the rightmost side is the mount that we. These are different types of mounts with different features and added functionalities. Now, when you are setting the camera, you have to choose the focal length or the camera. The particular camera should be chosen depending upon the object that you want to select. So out of the cameras that I showed you above, so this planetary cam has a sensor size of very maybe 5 mm or 3 mm or 5 mm, which is much less compared to the DSLR sensor. So the field of view that you will be able to capture using a planetary camera will be much less. So it is always a good idea to use this camera for photographing planets or moon or smaller objects like globular clusters. But you can use DSLR cameras and mobile cameras to capture wide field photos, maybe photos of some galaxies or nebulas or clusters. And CCD cameras are giving you an added feature of cooling, as well as it gives you an added advantage of very low noise. So we will move outside and we will see the different attachments, and we will see how we can attach those cameras to the telescope and acquire images from them. We'll stop sharing this presentation. Yeah. So right now, so you can read. So what you see here is the ZWO planetary camera. Okay. So this camera is a color camera, and what it does is it allows you to capture photographs using a direct CMOS sensor. So a little while ago, Samir mentioned you about different types of sensors. Is it clear? Yes. Okay. So this is the CMOS sensor, and when the light falls directly onto this CMOS sensor, the image is captured, and you can acquire the image using different softwares given by the camera manufacturer. And along with that, you can also write your own softwares using the ASCOM driver, which was also mentioned yesterday. So what I just attached to this camera is a 1.25 inch adapter or a reducer, which is very easily available in the market. And what I have done is, yesterday I had attached this eyepiece holder attachment on the telescope. So instead of that, I have removed it, and in place of the eyepiece, I can directly insert the planetary camera. Okay. So this is one of the types of cameras and one of the types of attachments. So we have another telescope over here, and on this telescope, I have attached a DSLR camera. So what happens for a DSLR camera is, we have an attachment called T-ring. So a few minutes ago, we had seen the image in the presentation. So this is the T-ring or the T adapter, and you can see all the attachments over here, the red dot. So once you match it to your camera model and attach it, it goes in place of the default camera lens. Now you can see the diameter of the T-ring is much larger as compared to the eyepiece holder. So you cannot attach it directly. So you need an additional 1.25 inch reducer here as well. So with help of these attachments, for some larger telescopes, you may not need to use this attachment. The telescope can directly thread in. The eyepiece holder of the telescopes can directly thread into the T-ring adapter or the T adapter of the camera. But that happens very rarely in case of some telescope models. For example, Skywatcher telescopes or GSO telescopes allow you to directly attach T-ring to the DSLR camera. The telescope. The camera is directly attached to the telescope. So what we can do is, now we can insert the camera instead of the eyepiece into the telescope. So this is yet another type of attachment. We also have a mobile phone adapter or mobile adapter. So what we can do, we have a phone. So what we can do is we can attach an eyepiece over here. So you can see this is an attachment. So I will get an eyepiece. So you must remember that we had seen this eyepiece yesterday. So what we want to do is we want to attach this eyepiece into the telescope. But while we are doing that, we want to ensure that the mobile phone should remain in front of this eyepiece while capturing the photos. Okay. So to do that, first let's affix the eyepiece onto the eyepiece adapter. So it has a variable length adjustment, so you can attach any eyepiece. So you don't have to purchase many eyepiece adapters or phone adapters for different eyepieces. Although there are some available in the market. So people will encourage you to purchase different eyepiece adapters for different eyepiece lengths. But you can get this universal adapter, which is also available. See, now we have flushed this eyepiece. So we have kept the eyepiece exactly in line with the surface, and we will affix it tightly because this eyepiece is going to take the weight of the mobile phone as well. So this attachment needs to be as firm as possible. Now this is a mobile phone, and depending upon the camera, the position of your camera, you will have to adjust this particular attachment. So you can loosen this screw, so it will change the width of this particular holder. Okay. So for this this particular mobile phone, the camera is on the corner. So you can also rotate this particular attachment, which will hold your phone. So I will fix the phone first. So make sure that your phone is fixed tightly, otherwise it is going to fall and it may crack. So now you can see the eyepiece is attached firmly, the phone is attached, and by rotating this phone, we have to exactly align. So we can switch on the camera now. You can see, is it visible? So you can see that the camera is on now. Now I need to bring it exactly in front of the eyepiece. Align the camera. It is aligned now. And once I align this, I have to tighten this particular bolt. So I have fixed this particular attachment. And now what I can do is I can insert this directly in place of the eyepiece. So this is the eyepiece. So this eyepiece will go back into the eyepiece holder. Here we go. So now our eyepiece adapter, the mobile phone adapter is connected to the telescope directly, and our mobile is ready to capture photos using eyepiece projection. Okay, so if I remove the lid, if I point the telescope outside, it is raining. It is still raining very heavily. Trees which are far away. So I will focus it now. So this is the rack and pinion I mentioned yesterday. So once you align the camera, you don't have to move it later on. Okay, so now we can see an image clearly. So I'm not sure if you are able to see, but the camera is now able to capture trees at a far away distance. Okay, the image of the image is not getting focused clearly, but you can get an idea that this mobile is now allowing you to capture photos using eyepiece projection. Okay, so this entire setup is called as a mobile phone eyepiece projection assembly. So if you purchase only the mobile adapter, it will cost less than 1,000 rupees. So I think this particular adapter was purchased at 500 or 550 rupees. You can easily get it on Amazon. If you don't want to purchase it, you can make your own adapter. You can just 3D print it, or you can make it yourself using different components that you get in hardware stores. So this is the mobile phone adapter. You also saw the planetary camera, which uses a 1.25-inch reducer and which has external threading. We also saw another type of an attachment, which was called the DSLR T-ring adapter or T adapter. So it also has a T-ring and a 1.25-inch reducer, which allows you to attach the DSLR camera directly to any telescope. So these all are standard attachments. So no matter where in the world you are, all the telescopes are going to support 1.25-inch adapters as well as a 2-inch adapter. Okay. So these are the different equipments or the ways you can connect your telescope to. Some cameras allow you to connect the camera directly to the laptop using wireless connectivity with the Wi-Fi or a Bluetooth, or you may have to use a cable which comes along with the camera. So using the cable and using different softwares, you can control your camera directly from the computer itself. And once you set up an interface, you will be able to get the image of the camera on the screen. So I will go back to the present and show you. Until then, you can catch the
Okay, so ZW, right?
Preview of the camera from the computer. Let's come back to this presentation. And let's look at a few important slides on selecting how you have to set particular camera settings. So we have created this moon sheet. Yes, so you can see that for different types of equipments, there is a checklist. So once you have cleared all of these checklist items, you are ready to photograph moon. So for lenses, for good quality moon photographs or a detailed photograph, lenses of greater than 300 mm are recommended. The moon, a very stable tripod is recommended. Not a tripod, any other attachment which will keep your camera fixed and as stable as possible. Then along with that, these are the few thumb rules that we have selected. So the aperture, if you keep it as f8 or f11, will produce fairly sharp photos, and decide the ISO at runtime. Depending upon the sky conditions there, the ISO can be adjusted at runtime. And a fair starting exposure is 100th of a second. If your will be changed a little bit depending upon the sky conditions. If there are clouds, then this ISO has to increase, or if not ISO, then at least the exposure has to increase. So these different trial and error methods can be used, but these are good starting settings for. And also it is a good idea to use spot metering. Right now, we will not go into all the details of what metering means, what ISO means, what aperture means, but you all these names on your DSLR cameras sometime or the other. Now, if you see the camera control softwares, these are some of the free softwares that I would like to recommend. So for Canon, the EOS Utility and DSLR Remote Pro are some softwares that you can use for camera control. So this is how the entire interface looks like. In this, you can see the camera live view, and you can also control all the parameters on the camera from your computer. These different softwares are also available for mobile phones. So if your camera has the capability to connect directly to your cell phone, you can also use your cell phone as a remote instead of a computer. Okay, so now let's also see a few more slides. Softwares. So what I will do is I will go back to the top of the presentation and we will come back in a flow. So until then, we will be ready with the setup and a preview. So this is how the cameras have evolved. Initially, we used to have the lens, the photographic plates. Then we used to have film cameras. After that came the film rolls, and then the SLRs and the DSLRs. So all these cameras had their own ways and different attachments using which you can connect those to the telescopes. And DSLR cameras are some of the most advanced now, and you can film cameras, and you don't have to wait to see your images. So the cameras function not like human eye. The human eye has a pupil, which is an opening, which allows the light to enter into our eye. And the lens has a similar opening, which is called as aperture. Okay, similar to the eye, the lens has a frontal element which protects dust from entering directly into the camera. And the iris muscles, which control the opening and closing of the aperture or the hole in your eye, there is a diaphragm in the camera which controls the aperture from opening and closing. So the functionality is much similar, or we can say it must have been inspired from the human eye. So there are three important settings that you need to watch out for. They are called as ISO, shutter speed, and aperture. Okay, on the camera, the ISO is written as ISO. The aperture will appear with a small indicator called as AV. Okay, so whenever you are changing the AV number, what you are doing is you are changing the aperture of the camera. Then there is another letter on your camera dial, which is called TV, or the time value. So when you change the TV number, you are changing the shutter speed. So shutter speed is the total amount of time that your camera is exposing the light, and it literally looks like a shutter. Okay, so what happens is a shutter slides, the camera sensor is exposed for a small amount of time, whatever the TV value is in seconds. And after the time elapses or the time ends, the shutter closes again. Okay, so this is called as the shutter speed. So although the shutter speed, it is actually a measure of time. So it is the duration for amount of which you have kept the camera shutter open or exposed. So with the combination of all these three ingredients, you are able to produce different images. So the shutter speed decides the motion blur. So if your object is fast moving like a satellite, then you will have to keep the shutter speed very less. So you can get a very clear and crisp image of the satellite. Otherwise, it will trail or it will drift in the image. The ISO also contributes to the overall amplification of the image. Okay, so ISO is something that is applied after the image is captured. In the initial times when there will by the density of the film. Okay, so but nowadays the ISO is applied digitally by amplifying the light signal on your digital SLRs. Then the depth of field. Okay, so you can get this idea over here. So when you get a camera lens, so there are these. So you can see this small circle, and there is 77 mm written here. So that is the overall lens diameter or the aperture of the frontal element, diameter of the frontal element. So here you can see the variable focal length, which is 24 to 70 mm. And so this 2.8 is nothing but the aperture value of your lens. So this aperture value is different for different focal lengths. So it is the overall size or the overall opening that your camera lens allows for the light to enter. So 2.8 is 2.8 millimeter aperture, and the lower the number, larger will be the. So you can see at 2.8 aperture, the closer objects are focused and the farther objects are blurred. So at f-stop f1.4, the aperture size is maximum, and whatever number is there written after the word f, that number is usually divided from the current focal length of your camera. Okay, so let's say if my aperture, you can see that the focal length divided by 16 becomes a very, very small number. And that is the opening of my camera lens, and that allows me to focus farther objects. So if the aperture is larger, I mean the opening is big, or the f number is less, the closer objects are focused. If the opening is small and f number is more, the farther objects are focused. Okay, so this is a very good example to illustrate that. And this is how the DSLR cameras work. So the light coming from far away object enters into the lens elements, and then the lens elements focus that light, and that light reaches onto the sensor. Okay, and for the light to reach the sensor, the shutter needs to open, and that shutter opening and closing time is decided by the shutter speed value or the TV value. So these are some of the examples of different shutter speeds. These are the types of photographs that you can take. Using long exposure photography, you can click photographs of objects like Milky Way, clear night skies in the sky. Along with that, you can also do this light painting. So I got a feedback that there is an echo in my voice. Let me just fix that. So there is another, like we said, ISO is nothing but the amplification in the image or the brightness of the image that you acquire. So by using different ISOs, you can enhance your image light. But along with the light, also the noise or the grains which are seen in the image are also enhanced. So you have to use this number judiciously. If you set too much ISO, then the noise is also going to increase too much. So also the number of light, the amount of light that you allow the camera to capture decides at what color the image you are going to acquire. So this also needs to be chosen wisely. So if you must have seen different colors of moons, right? So depending upon the white balance or depending upon the temperature of your image that is set, the color of the image changes. So if you set a white balance as a flash, then the image appears close to white. If you set the white balance of the image as a tungsten, then the image appears yellowish. Okay. So the white range is set to a certain temperature, and that temperature corresponds to some color in the spectrum. Okay. So using different temperatures or using different white balances will yield you different or different tones. So these different shades are basically called as color tones. And by deciding the type of white balance or temperature, your color tone will be decided. So again, this has to be chosen wisely depending upon the type of the object. So if you are capturing different colorful objects, these different color tones may suit. But if you are capturing bright white objects like the moon, then it is usually a good idea to select flash or maybe cloudy white balance. So it allows you to capture the real colors of the moon. And what is interesting is if you capture the enough amount of data coming from the moon, you can also enhance the colors on the moon, which are emitted because of the minerals present on it. Okay, we will be looking at some of the photographs. So these are some further details. So the more the focal length, less is the field of view. So you can see for a camera, for a 11 mm lens, the focal length, which is 11 mm, the field of view will be almost 180 degrees. So as you keep on increasing the focal length, the field of view keeps on decreasing. So this is a very nice illustration with 18 mm camera, the focal length is 100. Focal length of 18 millimeter camera, the field of view is 100 degrees. For 35 mm it is 62 degrees, and for 900 mm it is 3 degrees. Okay, so if you know, the size of the moon is around half a degree. So if you convert the 180 degrees of the sky, the moon will occupy only a half a degree area in the sky. So that is how much big the diameter of the moon is. So this is the relation between the focal length as well as the field of view. And you can see the more the focal length, more is the magnification. So we all have seen that, because magnification is defined by the length of objective or the length of the primary lens divided by the length of the eyepiece. In case of cameras, there is no eyepiece. So the distance between the lens element and the sensor is considered as fixed, which is usually close to 30 or 35 mm. So we saw these different attachments, we saw these different types of cameras, and for all the cameras that you see on the screen, there exist different types of adapters. And if there are no ready-made adapters, then you have additional attachments by yourself, and which will allow you to connect these cameras or different types of gadgets to your telescopes. Now, it is recommended that you use raw images instead of JPGs. So there is no compression and no. The Earth's rotation is what causes the trails inside your image. So in order to compensate for that, we use the mounts which use different types of trackings. Okay, so there are these different formulas that we have given. So to calculate the optimal exposures for a given lens focal length. So if you use these simple formulas and some simple tricks that we have given, you will be able to compute approximate exposure time, which will allow you to click wide field images without star trails. So for images like this, so this image was captured from Leh. This is further more detailed formula, which will give you an exact time in seconds. So for until how long your telescope will allow you to click photos without any trailing. Okay. If you have a tracking mount, then you can take images for 4 or 5 minutes, or probably even more, and you can get in your images. So this is the Lagoon Nebula, which is captured using a simple DSLR camera attached on a mount directly. So no telescope is used. A simple camera lens was used on a DSLR camera, and a long exposure photograph was taken. So you can see this is a overall 25-minute image. So 5 images were captured of 5 minutes each, and we have stacked those images on top of another. So it produces beautiful colors, and it also gives you too many details. So these we have used the equatorial mount for that, and to give a sense of field of view with respect to the Milky lens, you can get only a small part of the Milky Way galaxy. So what you see here on the screen is the area near the Sagittarius constellation, or on the top right hand side there is Scorpius constellation. So this is the center of the Milky Way, and to give a sense of the field of then there are different types of aberrations that are produced because of the lenses. These aberrations are a result of different reasons. So there is a chromatic aberration. The word chromatic literally suggests the word color. Then there is the chromatic around the bright objects. So that type of a aberration is known as chromatic aberration. A spherical aberration is one where around a bright source you can see these bright rings which keep on fading off. So problem in the optics of your telescope or your lens. Then there is a chromatic aberration where around the edges of the image you can see objects producing coma shape. So like the punctuation mark, comma. And then there is astigmatism. So this is another type of aberration that we experience. So this is the simple process that we follow. We locate the object, we take a sample photo, object is in the center. Then we click many photos of the same object instead of one large photo. Because what happens is if you take one single photo of a very large duration, then the object will, then the photo will also acquire a lot of noise because of the stray light, because of the temperature, and so many more reasons. So to avoid that, we take many photos of small durations and then we stack them. And once we do that, we get good results. So this is the kind of a noise that you get because of exposing the image for cover the lid of the camera, and you can see so much noise is there. So this is all the colored noise because the camera is a colored sensor. So to remove this noise, there are different types of processes and different types of processing algorithms are there. Many such single images when stacked together will produce this much detailed and finer image. So the process, we take different small exposure single images, we stack them, and after stacking, we do some processing on them and we enhance the data that has already been captured. Okay, so these are the different softwares we saw. This was the camera control software. These are their names. So I will be sharing all this, so you don't have to write anything down. Then there are these softwares that are used for stacking. These all are free softwares, and these are available on all platforms, including Linux, Mac, and Windows. Then there is, these are the free processing softwares. Okay, so these all softwares allow you to enhance different images and perform different operations on your photos. So there are different processing mechanisms for different types of objects, and it involves a lot of details. So that is something that you can find out on your own very easily nowadays. These are some softwares for processing. So some of them are free, some of them are paid. So this is the result of whatever I just said. So what we did was we clicked 3 different photographs of the moon. So the first photograph was a very low exposure photograph, underexposed photo. And the third, and then we put all these 3 photos together, and then we created a composite of the moon. Okay, so from the overexposed photo, we were able to get this left-hand side feature of the moon called as the earth shine. Okay, so ideally the moon does not receive sunlight in this region. But if you take a long exposure photograph, what happens is some part of the sunlight enters into the Earth's atmosphere, and the Earth's atmosphere refracts that light, and that light reaches up to the dark area of the moon. Okay, so that region, that particular part of the moon is said to be in the earth shine. And then there is the part of the moon which is illuminated, which is directly receiving sunlight. So you can see beautiful craters along the line which divides the dark and the bright part, called as the terminator line. And you can see different colors over here. So these are not false colors. We have not done those colors, what we have done is we have just enhanced the existing colors that were captured by the camera in itself. So we increased the saturation of the image, and we enhanced all the colors that were already there on the moon. So these different colors are a result of different minerals which are present on the moon. The questions as we go, so we don't have to wait up after. Is astigmatism the same phenomenon that one can see if the eyelids are narrowed? Kind of. So it is a result of the spherical aberration and basically the deformation in the lens. So the effect is similar, but the reason is not. The reason is because of the error during the manufacturing of the lens. We can stack these images using all the open source softwares that I had told about. So one of the excellent software is Deep Sky Stacker. Sequator is another software, and Cyril is yet another software. Stack different images of different objects. Then how is a SLR camera different from a DSLR camera? So this is a very simple and a factual question, and you can get this answer as soon as you search images of both of these cameras. You can immediately figure it out. The additional component to a digital SLR camera is that you can see the preview of the image that you get. For a SLR camera, there are usually films, and you have to process the film or develop the film, and then you can get the images. For DSLR cameras, although the arrangement of the lenses and all the sensors and everything is same, instead of the camera sensor, an SLR camera uses a film, and a DSLR camera uses a sensor. Photoshop or Lightroom are often used for the post-processing or further enhancing. So to bring out these colors and to bring out these added features on the moon or stitch these images together, Photoshop and Lightroom can give you some excellent presets and some excellent tools, which will make it very easier for you to do that. Although there are some open source tools or free tools like GNU Image Manipulation Program, which is available on Linux, Mac, and Windows. It will also allow you to do all of that, but and open source softwares as well. So I definitely always recommend using free and open source softwares. But yes, you can do all these same processes using them. So these are some close-ups taken using the planetary camera. So this region these are two different images, by the way. So on the left-hand side, there is one image. On the right-hand side, both of the images are closer to the terminator line. You can see a mountain range over here, and you can see the shadows of the mountains casted onto the surface of the moon. And you can also see many craters over here, so which are highlighted, and you can see them in very good details because of the contrast of the terminator line. So the photo on the left hand side is taken by a cell phone. Okay, so using the mobile phone adapter in front of the eyepiece, and we have clicked a few photographs, and this was one of those images. Then you can also do planetary photography. So this is Mercury. So you can see, just like the moon, Mercury and Venus, this is planet Venus. So this is a very important exercise that you can try. So maybe whenever clouds will allow you, you can see the different phases of these planets and see what phase Venus and Mercury are in today, or maybe in the coming week. Then you can also do these different planetary photographies. If you do not have a planetary camera, you will have to go for eyepiece projection method, where the eyepiece will take care of magnifying your image, and your sensor will take care of capturing. So even though we capture cosmic images with very high resolutions, while printing, their sharpness goes away. So the reason is that whenever you click an image, the image is captured at some very low resolution, whichever is supported by the camera sensor. So usually whenever you are capturing the image of a large object, so Anushka has asked this question, that even though we capture images in very high resolutions, the photographs will lose their sharpness. That you have to take care is that you don't stretch or you don't magnify the photographs too much. And if you are taking photograph of a large object, use the method that panoramas use. So if there is a very large object, click smaller pieces of that object and stitch those pieces. So when you do that, you can get clear images like this. So this is done by using by clicking different photographs of different regions of the moon, and then we have stitched those regions together like a jigsaw puzzle. So this is called as a lunar composite image or stitching. So you can also search about lunar composite and produce these very high resolution images, which when you even try to print will not pixelate. So you can also capture different events like conjunctions, occultations, and cameras and basic setups can be made available or can be used directly for. So there are these some rare visitors known as comets, and you can also capture these comets. So this is another famous popular type of photography called star trail photography. In the foreground, you can see the IUCAA Giravli Observatory. Just behind that, you can see a star trail. It's red colored lines. So these are the different aeroplane times. So what we have done is we have clicked many photographs of the sky after equal intervals of time. And then we uploaded all these photographs on this StarStack software. So this is a free open source software. I think it is available on Windows only, but I'm sure there should be something available on Mac and Linux as well. If not, you can use the and you can stack those images together at once. So using this method, what you can do is you can stitch or stack all, and you can take a good clear foreground image and post that image on top of it. So you get this beautiful star trails. So this is these are the star trails taken from Sinhagad. This is taken from Raj. These Sinhagad and Rajgad are forts very close to Pune city. Both of these photographs are taken by mobile phone. So it is not at all necessary to have very high-end equipments or DSLR cameras. You can also produce these photographs, beautiful photographs, using mobile phone cameras. So this is the Milky Way galaxy, which is a 2-minute photo, and there are 10 such exposures which have been put together. More examples of Milky Way. This is the satellite pass. On the top left, you can see many streaks of images. So this is taken from the terrace of IUCAA Science Center. And this is basically the International Space Station traveling from north to south. On the top right-hand side, there is an Iridium flare. So Iridium is a communication company, and they had a lot of satellites who used to produce flares because of the sunlight getting reflected from their antennas. So if you were looking at an Iridium satellite, the Iridium satellites would turn constantly into their orbit. So when these satellites turn, they have very large antennas, and those antennas reflect sunlight. So when you're looking at them from Earth, it appears like there is a small flash. So these phenomenon were known as Iridium flares. You don't see these Iridium flares anymore because the satellites have now begun to decommission. But if you are lucky, you can still see a couple of other satellites. Then this photo at the bottom is taken using a cell phone. So again, you don't need any expensive equipment. You can just use your cell phone cameras, which are now very modern, and you can use them using different tools, different applications, or some of the mobile phones also support taking long exposures directly. So this is a lucky shot. So we were capturing the photo of Whirlpool galaxy, and a meteor passed from the diagonally from our frame. So this is another type of wide field photography. You can also do a time-lapse photography during certain events. So this was taken during the Venus transit, and this was taken during the lunar eclipse. So there is a lunar eclipse upcoming on 20. So if we are planning to do some event, then we will definitely let you know. I will wrap up in another at the most 1 or 2 minutes. So this is another type of photography that you can try. So capturing the same photo at different times of the day and putting them together, stitching them together. So the principle is the same as star trails, but in the star trails, you have continuous photographs with no larger gaps in between them. So for these photographs, the gaps can be larger, and then you simply So for solar photography, like Samir sir mentioned a while ago, you have to be very, very careful. You should never use your telescope or a camera to look directly at the sun. Otherwise, it will be damaged permanently. So you have to use appropriate solar filters. So you can, using solar filters, you can do this type of photography during some interesting events. So these are the mobile phone apps. Somebody just asked a question about mobile app. So my shutters open for maximum 32 seconds. So you can use these different mobile apps which allow you to use your camera to their smartphone camera to their full potential. So try this out and you can experiment. So these are some more photographs that we had captured using DSLR cameras attached to the telescopes. And even you can do this. This is quite easy to do. Although the processing is a bit tedious, but you can of course learn. So I wanted to show these photographs. Rosette Nebula. The preview is ready from ZW camera. So this is our last slide. So the most important thing is there are many excuses to not take photographs. There is bad weather, inadequate gear. Many times it is. So the most important thing is to start. And as you keep on trying, you will keep on improving. So don't worry about whatever equipment you have. No matter how simple your camera is, no matter how older your camera is, there is always a way to utilize it. And there is always a way to take good photographs using your image. So this is the way to contact us. If you have any questions, please feel free to write us on saipop@gmail.com. And I will encourage and request you all to please follow all these social media channels. So whenever we are arranging any event or whenever we are arranging any demonstration, you will be the first to know about the updates. So these are our social media channels. This is our website and this is our email ID. So don't forget to write us. Right now, what I will do is I will stop my screen sharing. Is the camera ready? Mobile. Right. So we have spotlight the camera outside. So we have attached the ZW camera to the telescope, and using the USB port, we have connected to our computer. Now, whatever our telescope is seeing, that preview of that telescope will appear onto the laptop screen. So we are using the StarCap software. So right now.
Hello, Atharva.
There is no voice. Okay, am I audible now?
Yes.
Okay, I will. Main master. Right. So what we have done is, you can see the camera, ZW camera attached to this telescope. So this camera is attached in place of the eyepiece using the adapter that I showed you earlier. Now the telescope is just randomly looking outside, and you will be able to see that it is raining outside quite heavily. So just to give you a sense of preview, whatever image the camera is looking at can be accessed using a camera control software. In case of a ZWO, we are using an open source software called SharpCap. And you can see when I cover up the telescope, the preview will change. So if it were a little bit clear, I could have gone outside and shown you some images of the terrestrial objects. But this is how you can get the preview, and this is how you can control the camera using a computer. And there are similar softwares available for DSLR cameras as well. So using those softwares, we can capture different images and we can produce some beautiful results. So I think So I think with that we can conclude today's session. But if there are more, if not, you can. If you cannot think of the questions right away, you can email it to us later on sipop@gmail.com. So in our chat window, I'm posting our email ID. And whatever presentation that I was showing you guys right now, I will share that presentation with you all right away. So that link also I'm sharing in the chat window. So until then, if you have any more questions, you can feel free to ask, or we can conclude today's session. So thank you all for listening. So this is the link of the presentation that I was showing. I will share it with the organizers, and we will all make sure that it reaches you. Somebody was asking for yesterday's recording, so perhaps somebody from the organizing committee can clarify that. So thank you again for these for listening to us. So I would like to request Sagar to please conclude and end the meeting.
Yeah, sure.